We're still talking about measures of variability. I'm Alex Wiseman, and we were finishing up with a discussion about how we might look at calculating some probabilities of scores under the normal curve. And we looked at how we might calculate between scores, like what's the probability of a score falling between this z-score and this z-score. And we talked about calculating the probability that things are on the outside of a range. And we can calculate this area and this area and simply add them together. For example, this would be 10% plus 10%, 20% chance of falling outside of these z-scores. I'm actually going to skip over this, I think. But if we wanted to, we know how to calculate z-scores. Right? We could calculate the z-score for 11.2 given the mean and the standard deviation. And we know if we tested 1,000 randomly selected students, how many would be expected to score 5 or lower. That's simply our percentage frequency that we could take from our normal distribution. And then we could calculate reading scores that correspond to percentile ranks of 75% or 30% using those simple calculations from before. What's most important to recognize, however, is that when we're calculating percentile ranks, we're using the standardized score, which is a measure of how many standard deviations from the mean a score is, and we're simply calculating the area under the normal curve that falls either above that score or below that score or between a set of z-scores. So that's what percentile ranks are. That's what it means to calculate the probability of a particular score falling within a particular range. And so when we get to, sorry, it's messy on this. Let me take off the extra ink. When we get to calculating statistical significance, we're going to be calculating the chance that there's more than a 5% probability of a score falling somewhere on the outside of our distribution. And remember, we call these tails, either end of the distribution. So you can do something called a one-tailed test of statistical significance or a two-tailed test of statistical significance. We haven't gotten to that yet, but this is all part of the same conversation. So is there more than a 5% chance that something is falling outside of this normal area? And it's a pretty big area we're giving ourselves. Only 5%. That'd be 2.5% on this side and 2.5% on this side. Very low chance if it's two-tailed. Okay, so conceptually that's what we're doing, and we'll be moving forward with that. Moving past this to, hey, guess what we're going to do now? We're going to talk about kinds of distributions. So there are three kinds of distributions that we can generally think about. One is a population distribution, and that's simply the distributions of all the scores on a particular variable in a population. There's a sample distribution, or distribution of a sample, which, guess what, is the distribution of scores in a sample of a given size. And then we have something that we can more specifically call the sampling distribution, which is the distribution of some statistic, for example the mean, in all possible samples of a given size. So you can see how it sort of steps down and becomes more and more specific. And this is when we can start talking about something called the sampling distribution of means, which is simply a distribution whose scores are means of samples drawn from some larger population. Well, how do we calculate or construct a sampling distribution of means? We simply draw a sample of a certain size, we calculate the mean of the sample, and we repeat, right? We repeat that over and over for a large number of samples out of the larger population, and then we can plot that in the form of a frequency polygon. Guess what that looks like? So for example, we might have this population, and we take sample after sample after sample after sample after sample. We calculate the mean for each one, and then we simply talk about the distribution of those means. Now, what are some of the properties of a sampling distribution of means? Well, the mean of all sample means equals the mean of the parent population. So if we were to take the mean of all these means, I know this sounds redundant, it would equal the mean of the population. This is something that we are eventually going to call a central limit theorem, and this is a simplified version of that. Right? The central limit theorem simply says as the sample size n increases, so the number of samples, the sampling distribution of the mean more and more closely resembles a normal distribution. So for example, with only 5 means here, we might come up with a skewed distribution, much like the homework distributions that I showed in a previous screencast in this variability series. But if we have, let's say, 100 samples, and we calculate the means for each of those 100 samples, and we plot that, it's going to look more like a normal distribution. If we have 1,000 samples from this same population, and we calculate all the means for those 1,000 samples and we plot them, it's going to look very much like a normal distribution. Right? That is the central limit theorem. As the sample size n increases, meaning that you have more and more samples drawn from the population that you're taking the mean of, then the sampling distribution of the mean more and more closely resembles the normal distribution. Why do we care? Well, we care because this helps us calculate something called the standard error of the mean. And it is simply a standard deviation of the sampling distribution of means. So the standard error of the mean has this fancy Greek symbol, and it's simply the standard deviation of the means divided by the square root of n. Right? Now, we rarely have all of these samples, right? An infinite number of samples that we can calculate for the population. So what we instead do is an estimated standard error of the mean, which is the same equation as before, except we've replaced this fancy Greek symbol with an S. And we talk about the standard error of the mean because it gives us a way to talk about variability in the distribution of a population at large. It will also help us calculate confidence intervals. Confidence intervals are a range of values within which we're reasonably certain that the population mean lies. We also sometimes call this the margin of error. You're probably most familiar with this from polls. Polls will often report what they find and then say the margin of error is, +5 or -5 or something like that. Okay. Here's what we know. We know that in a normal distribution, 95% of all scores lie within 1.96 standard deviations from the mean. 0, 1, 2, 3, -1, -2, -3. So 1.96. That's almost. In fact, I should change the color. Let me change the color because I can. There's blue. So almost at 2 and almost at 2. 95% of the scores are going to fall in this area. So all we have to do is subtract 1.96 standard errors from the sample mean to find the lower limit. And then we add 1.96 standard errors to the sample mean to find the upper limit. All right? So a 95% confidence interval is the mean plus or minus 1.96 times the standard error. If we wanted to get crazier, we know that 99% of all scores lie within 2.58 standard deviations from the mean. So here we go again. 2.58, there's 0. I'll just say this is 2.58. This is -2.58. 99% of all scores are in here. So what do? Subtract 2.58 standard errors from the sample mean to find the lower limit, and then we add 2.58 standard errors to the sample mean to find the upper limit, and we come up with this fancy little equation here. So suppose that 18 college students have had 3 homework assignments and their average scores were computed with the result that the mean is 80.46, the standard deviation is 17.46, what are the 95 and 99% confidence intervals? Well, what information are we given? We're given the mean, we're given the standard deviation, we're given the fact that we want to calculate that. What do we need to calculate this? Okay, that's, by the way, something for you to think about. You have the formulas, you know how to calculate them, right? Standard error of the mean is simply the standard deviation divided by the square root of n. I should also point out that you have the n right here. You have all the information necessary to calculate the 95 and the 99% confidence intervals. If we had something a little more, if we made this more complicated, I'm not asking you to compute this, but I'm saying that you could. We've got the sum of x, excuse me, their scores, and we got the sum of their scores squared. We could also calculate the 95 and 99% confidence intervals for the population mean, because we have these fancy computational formulas. Now, the point of all of this is not to get you to whip out your calculator and start calculating this. The point is to help you understand that constantly we're talking about kind of variations on the same theme. When we talk about measures of central tendency and measures of variability, we say that these are descriptive statistics because we're describing the sample. And that's what we're doing here. But it tells us so much about the sample. It's more than just saying, well, the mean is 5 and the standard deviation is 1. Right? It has much more to do with that. We can now start to estimate, or to actually, it's not estimating, we can just say that a score is, at the 99th percentile rank, because we know that it is higher than or equal to 99% of the rest of the scores in our particular sample. We can say that there is a range of scores that will fall within a particular difference between two. We can standardize scores so that we can compare them even if they are using a different set of values, like if the range of scores in a particular set is different, or any of that. So we have a lot of capability to have interesting information just from measures of central tendency and measures of variability. All right, I got excited about that. Let me just finish off by talking very briefly about kinds of sampling, and then I think we'll be done with measures of variability. There are some kinds of sampling that we should be aware of, and there are many more that you will find in, just pick up any research text, any educational research textbook. You will find at least a chapter on sampling. I don't think you need that much to start. One is, you really have two kinds of sampling, either representative or unrepresentative. Representative is going to try to be randomly sampled, because that will give the most chance for each person or individual case or whatever in your larger population to be represented in your sample. The other kind is unrepresented, and it's biased. And often we have a reason for doing that. It's a purposeful sample. Hey, I want to find out what Joe Bob did, so I'm going to sample Joe Bob. Okay, it's biased. I know that. It's not random. I know that. It's okay as long as I'm honest about that. The only time we need to worry about representative samples is if we want to generalize to the larger population. If we don't care about generalizing to the larger population, then it doesn't matter. Use unrepresentative. The way, however, that we make a sample representative is through random sampling. And we can do that with or without replacement. Let's imagine I have a bowl. And in my bowl, I think I have this. Let's imagine I have a plate, a plate full of marbles. And I take one of these marbles out. Let's say I started with 100, and I took one out. What's the chance of me pulling that one out? 1 out of 100. If I keep that one out, how many are left? 99. If I pull another one out, what's my chance? If there are only 99, it's 1 out of 99. So my chance of pulling the second one out is actually greater than the first one. That is called sampling without replacement. However, if I stick this one back in, we now have 100 in here again. And my chance of pulling this one out is not 1 out of 99 anymore, it's 1 out of 100. This is called sampling with replacement. And what we always want to do is we want to sample with replacement as much as possible. This will give you a start. Have fun.